Hey, it's Jim, and this is FRM Part 1, Book 2, Quantitative Analysis, the reading on machine learning and prediction, and this is Part B. Hopefully you've just watched that, 35 or 40-minute recording in Part A, and we'll do similar stuff here in Part B. Let me just quickly refresh your memory. What did we do? Some lasso, we did some ridge regression, we did some logistic regression, and essentially, we were in kind of part 2 of machine learning. And so we're just going to continue along, learn a couple of new concepts. We'll talk about decision trees. That's going to be super important. We'll do ensemble learning. I think that's fascinating. And then we'll end with, just a pretty cool conversation about neural networks. So let's go ahead and start with decision trees. And I'm going to go ahead and ask you to recall our decision trees for computing the price of a bond, especially the price of a bond that has an embedded option. But our decision tree in bond price as a bond pricing model looked like this, right? We had a point. Imagine my wrist as a point, and then we had all these branches going out, and we had a bunch of branches, and at each branch there was a node. And for a bond that had an embedded option, like a call option, we had to make a decision at each node. Now, this was a super simple decision. It was, will the bond be called at that particular interest rate? And the answer was either yes or no. So decision trees here in machine learning are similar. However, they don't go this way. They go this way. So what we're going to do is we're going to start at the top, and we're going to ask a question. And then we're going to work our way down to the bottom, and there's going to be different nodes that lead us to some kind of a decision. So there's an initial root node, decision nodes, and then terminal nodes. After the terminal node or nodes, then there's nothing else that follows. And so, in that callable bond decision tree, we call that an interest rate tree, that at each node we had an obvious decision. It was either the bond is called or it's not called. Here, the decision is going to be determined by an algorithm that somebody who's way smarter than I am, maybe even smarter than you guys, although I'm guessing some of you are writing these algorithms, who will write to make a determination. Now, bond pricing doesn't really lend us to machine learning models, although you can do that because it's relatively simple. But if we wanted to go back and take a look at whether or not a bond will default, so that brings in an entire specter of extra features inside of that model. For example, of course, we need to know what the operating cash flows are of the firm, what's the debt equity ratio, what's the quality of the management, what are its products lines look like, et cetera, et cetera. So you can see how much more complex the decision tree is inside of the machine learning world rather than just in that regular old interest rate tree world. Now, look at that little graph down at the bottom, that illustration. So there you can see the branches of the tree are moving downward. So a lot of times this is referred to a classification and regression tree because essentially we're going to try to find out what kind of a class can we put this input into. For example, look on that illustration. Down at the bottom, we're trying to decide whether or not a firm is going to pay a dividend or not. So what are some features? Profitability and free cash flow. Those are just 2 of them. What did I say just earlier? I listed maybe 4 or 5 of them pretty quickly. So this is a relatively simple example. And so imagine throwing those extra features into this model. Well, you can get a relatively complex tree. Now, what we want to do is that we want to take a look at this tree. Here, let me go back here quickly. Imagine that there are lots and lots of different colored boxes. And so this little flow chart here, this downward looking tree is way more complex. What we want to do is we want to make sure that at each of these nodes, when we're answering the question, and of course these are just simple answers, right? Profits greater than 1.5 million. That's just a yes or no. But we can make these much more complex and then we can learn as a machine, right? I've said this to you before. I can't help but think of Arnold Schwarzenegger in The Terminator. He never really quite learned. He tried to learn. He tried to gain a personality in that Terminator Genesis movie, but he couldn't quite pull it off. But remember, this machine is going to learn, and it's going to try to figure out how it can make better decisions as it goes through more and more iterations. Remember, these iterations are taking place very quickly. So this brings into this concept of an information gain. And so think about this. In this simple model, if every time a firm that had profits in excess of 1.5 million, and every time that particular firm had free cash flow growth in excess of 10%, if every time that firm issued dividends or increased its dividends or whatever it is that we're trying as our output or that terminal node, if every time that was totally accurate, well, then there would be no information gain, right? Then the model had learned perfectly about this. But as you split, and let me go back here just once again, as you split these answers to yes and no and yes and no and yes and no, clearly the machine is going to make mistakes. So how do we determine what that information gain is? And we do this in one of two ways, through the Gini coefficient or through entropy. Now, what we're going to do here, let me quickly go through this. Let me show you this here. We're going to do a base entropy example, but I didn't want to forget to say this. The reading has a Gini coefficient example, so I want you to go to the reading and work through that. It's relatively simple, especially after you see how we go through entropy, which I think is just a little bit more complex. So you'll have our example here, which doesn't show up in the reading. You'll have the readings example, so you'll have both of these. Now, the interesting thing is that at the end of the reading, there is an entropy example, but not a G coefficient example. So you guys, I don't know, you can determine whether or not you want to study both or learn both. It's interesting. And let me go back here to the very beginning. Whoops. Show how a decision tree is constructed and interpreted. So that's the learning objective. So I'm really not sure what the show means. It doesn't explicitly say compute or calculate, but I do know that demonstrate and show, they kind of mean the same thing. Oftentimes, these organizations mean go ahead and calculate while you're showing, or showing means that you have to calculate. So if this were me, I would be prepared to do both of these, and hopefully you'll see how relatively simple they are. All right, so what are we trying to do? Look at the goal at the bottom. Choose the feature that results in the greatest reduction in the measures, which means that we're the most useful feature in predicting that target variable, which back here was whether the firm pays a dividend or does not. All right, so let's go ahead and work through just a quick example. Let's first do the equations here. So there's entropy. So we're summing from I equals 1 to k. K is total number of possible outcomes. And notice we're taking the probability of that outcome and then the base 2 log of that probability. What that does, of course, those of you who know a little bit about math, that forces the range from 0 to 1, much like it did back with our logistic regression. Here is the Gini coefficient. So this is 1 minus the sum of those probabilities squared. So if you just take a look at these two things, we're summing, and there's the log 2, and there's probabilities. Here, there's probability squared here. What's interesting is that the reading makes a fascinating concluding statement that these two measures typically result in very, very similar outcomes. So there's not much of an advantage to using one or the other. That's why I think the reading does the Gini coefficient and asks you to do this on one of the end of reading problems. All right, so let's take a quick example here. Look at part A. We're going to calculate the base entropy, and then we're going to go ahead and illustrate the tree structure. So we're going to need our calculator. And we're going to need our ability to view in columns. All right, so look at the table. So we have credit card holders defaulting. So what is that? A total of 8 in that column. So there are 3 out of 8 who defaulted. There were 4 out of those 8 who had high levels of income. There are 4 out of 8 who had late payments. So what are we doing with these features over here? We're going to try to use those features to see if they contribute to our ability to classify or predict whether or not a particular loan will default. So remember, the goal here is classification and prediction. Sometimes they mean the same thing. We can predict from their class, or we can just make a prediction outright. All right, so here is our entropy formula again, right there in the gray box. And let's go down to the second embedded circle point. There are 3 credit card holders who defaulted and the rest who did not. So let's go back here, defaulted. So there are 3 out of the 8 who defaulted, all right? So we're gonna use that in our entropy formula. So we need to put the minus sign out there. And there's the summation, so there's a plus sign in there. We're gonna take 3/8, which is the probability piece of I, times the base 2 log of 3/8 plus 5/8 who did not, and then times the base of log 2 of those 5/8. Now, notice what we've done for you. We've given you the answer of 0.954. So here's where I'm going to go ahead and say to you, you guys need to figure this out on your own. I would learn how to do this. In fact, I've done this in 2 ways. There are a multitude of entropy calculators online, and you can easily Google those, and you'll just be able to type in the 3/8 and it'll give you the answer of 954. Of course, that doesn't really help you taking the exam. You need one of your financial calculators. So my advice is to go ahead and type in, do a search that says, how do you use the natural log, right? Each of the 3 financial calculators that you can use on the exam has the ln button. And really all you do is take the ln of whatever we're doing. In this case, it would be 3/8 divided by the ln of 2. This is the base of 2. And that ratio will give you the entropy in between each plus signs. If you sum them, you'll get 0.954. So I actually did this when I woke up this morning to make sure that the calculator actually works with the natural log function. And of course it does. Now my guess is that you might be given a table with that level of entropy here, 0.954. All right. All right, so let's go ahead and look at a couple of different steps here. Let's suppose that we examine the high income feature first. So let me go back here. And for some reason, we're just saying, and remember, this is the cool thing about machine learning. You don't really have to have any theoretical or economic model that says, hey, I think high income is more important than a late payment history. You don't need any economic foundation to say, I think late payment history is more important than high income. You just tell the machine, you just say, hey, you know what, pick one. And we don't really need to tell it what to do. So let's go ahead and say we examine the high income feature first. So we can go back and we can look at the high income feature. So, well, let me go back and do that. So high income, we've got 1, 2, 3, 4. So 4 high income people, 4 high income individual credit card holders had high income, the other ones had low income, and then just look at the match there. So there's 1 that defaulted, there's another 1 defaulted, and there's 2 that didn't default. All right, so that means 2 defaulted while 2 did not. So there's the entropy, and that of course it has to sum to 1 just by regular old common sense. But among the non-high income credit card owners, right, feature equals 0, 1 defaulted and 3 did not. I won't go back to that previous slide. You guys just take my word for it. And so that entropy turns out to be 0.811. So what did I say earlier? I'm guessing that you would have a table where you're given the 954 and you're given the 811, and they say something like, go ahead and compute the information gain. Well, you can easily compute the entropy there. 906. Information gain is the 954, 906, and there's the 048. Wow, there's an information gain by, well, let's go back here, putting the high income feature first. So what do we need to do? Let's go ahead and tell the machine, well, whichever one you picked first, which was high income, go ahead and pick the other one second, which was the late payment feature. So you go through all this stuff that we did before, and you get up at the top information gain 954 minus the 4055. Wow, so that's 5485. So look at that first bullet point there. The entropy is maximized when the sample is first split by the late payments feature. Wow, this is going to become the root node of the decision tree, and you'll see that in the next slide. Here it is. So we come in, here's our tree. Now remember, this is just super simple. We're going to start with the late payments, and so if the answer is no, well, then we just move on with our lives, right? So let's just go back here. Let me show you this just quickly. So if the answer is no, we've got, look at the zeros there, and what are we seeing? Wow. None of those people defaulted. So that is reflected in our tree. If no goes over here, then there's no way that they're going to default. Now, of course, we just have eight observations in this, in a real live tree. We might have 8,000 or 80,000 or whatever it is. So then, yes, then we break over to high income, and then yes or no, and then we arrive at our final terminal node down there on the bottom. So I think that first part is really cool. In fact, I would say that that's enough for an entire reading. I wouldn't mind going through a couple of extra examples, but of course the learning objectives are going to then say, well, you know what? We've done a bunch of models both back in part A, and now we did those entropy and the G coefficient. So there's two. We only did one, but you can go back to the reading again and take a look at that example. So we've done those two plus the other ones. How about if we take a step back and say, you know what? I wonder what would happen if we did this multiple times with each of these models and then throw them together. This is called an ensemble technique. And really, all we're going to do when we take the ensemble technique is to put these different trees together, get a final node, maybe we'll have 10, and then we're just going to take an average. And that's pretty much what the ensemble approach is. This is based on law of large numbers. So what we're going to do, the overall prediction accuracy, it tends to improve. So I think the good exam questions are, better performance and less prone to overfitting. Now, we did overfitting back in the previous reading, and we know how the complexification of these models are, especially when we overfit, and then we have problems with bias, and we have problems with variability. So less prone to overfitting. I think those are really two good answers for an exam question. Now, the follow-up question then is, how can we do this? So we're going to have bootstrapping, we're going to have random forests, and we're going to have boosting. So here, step 1, step 2, step 3. This is exactly what I was just saying to you a second ago. Ready? Sample the trading data, construct a decision tree, and then combine the predictions. Look at the very last sentence down there. We're going to average to make a final forecast. So really, that's what this bootstrap aggregation is. Don't get this confused with bootstrapping when we did interest rates and interest rate trees back when we did bond pricing. This is a little bit different. It's the same kind of a process, but it ends with just taking an average. Now, what I thought was interesting is random forests and boosting. This takes up just two small paragraphs in the reading, and quite frankly, I was a little disappointed that there wasn't more details. But I guess that's good for those of us who are taking the exam. All right, so a random forest is an ensemble of decision trees. So we have a tree. So think about what a forest means. You just throw a bunch of other trees in there, and you do this on different subsets of data. So you might collect 50,000 data points, and you might construct a tree on 10,000, and then 10,000 different ones, and 10,000 and 10,000. Does that add up to 50,000? So you get 5 of these, and then you combine them to form a more accurate final prediction. Now, boosting, this is a different kind of a story. What we do is we say, you know what, we're going to stink at first when we do machine learning. Whether we have the algorithm in there or whether we have programmed an agent in there to do our decision making for us, we're going to have some poor models. And so what we do is we have a series of weak models. So we know this model is weak, this one and this one, they stink, right? We're not getting anything out of them. But what we can do is we can compute the error terms of those models, and we can learn from those error terms. There's a lot of information, and we learned this back in classical econometrics. There's a lot of information contained in the error term. I remember when I was in graduate school, our professor, he always called it the disturbance term. And he would tell us, he would say, you know what? When you take the expected value of it, the expected value of that final term there is 0. And I used to always think, okay, it's 0. Let's just forget about it. And of course, I was trying to take a shortcut, right? Mr. Heuristic I was back in the old days. And the professor kept saying, look, there's so much that you can learn from this error. And it finally dawned on me, he would say, look, Jim, I know you used to be an athlete. Didn't you make mistakes and learn from your mistakes, whether it was on the football field or the basketball court? And I would think, oh my gosh, there we go. There's the light. So we can learn from the error terms, and we can build a better model. So we can turn a weak model into a powerful model to get rid of biases and lots of variance in there. So that's what boosting is. 2 kinds of boosts. There's adaptive boosting, and this is where what we're trying to do inside of these disturbance terms or the errors terms is saying, let's identify which of those caused us the most problems. As I grew older and had children, I'm watching my children, especially play basketball. All my children, 3 of my children are right-handed. Some of them are left-handed. But I had all of them learn how to dribble with their offhand and shoot offhanded layups. And, so what do you see when you're watching kids that are, 3rd grade and 5th grade? I mean, hardly any of them can make a layup with their weak hand. So what do? You practice. And so that's one way of becoming a good basketball player. So that's what we're doing inside of this model. If we have a terrible model, let's go back to the dividend paying model. Suppose that free cash flow and, what was that first one? Profitability. Suppose those were totally irrelevant, for some crazy reason. Well, we have to learn from that, but there's probably something in there that's going to help us learn. And that's what the adaptive boosting is, right? So look at that last bolded point, based on the performance of the previous classifier. So we're going to learn from the mistakes. Now, what the gradient boosting is, on the other hand, is that we're going to still use our error terms. But what we're going to do is we're going to put this algorithm so that we're overcoming some kind of a predetermined threshold. Like in our previous example with the dividends, we could say something like, we want a threshold of 75% accurate prediction, or whatever that could be. And we train the agent to make those decisions, so we get to that 75%. So the gradient boosting, in my estimation, is a little bit more specific than the generalization of the adaptive boost. All right, moving on to another learning objective. There's a relatively short section on the K nearest neighbor, and we have some illustrations here. These, by the way, don't show up in the reading, but these are really, really super helpful. K nearest neighbors, the K, this is kind of like clustering that we did back in the previous reading, but it's not so much clustering here as in trying to figure out who our neighbors are And what kind of features do those neighbors have? And do we fit in? Do we fit into that thing, K nearest neighbor? And so essentially what we're doing, and this, I tell my students this all the time whenever we talk about quantitative methods, is that what we're doing in classical econometrics and in machine learning is we're really just getting our ruler out. We're getting our ruler out and measuring the distance between one observed variable and how it fits in. What's the distance between its K nearest neighbors? And we don't really know how many K is. K is, there's some kind of a general estimate about K should be the square root of the number of observations. I guess that's as good a starting point as any. But notice the second bullet point there, the second block point, Euclidean distance or Manhattan distance. We did that, I think, back in the previous reading. So go ahead and remind yourselves, Euclidean distance is the straight line, Manhattan distance is the city block. And so you can measure distance in any way. But essentially what's happening here is you're trying to find neighbors that look an awful lot like whatever that observation is. In our example, a dividend-paying firm. What does that dividend-paying firm look like? Does it have lots and lots of net income? Does it have lots and lots of free cash flow growth? Does it have a low debt equity ratio? Does it have a majority independent board of directors? Does it have, what are those things? So you classify it based on its K nearest neighbor. So this is relatively cool. But I really like this SVM idea. So think about, just look at the graph over here. Think about the red circles and look at the blue circles over there. Think about these as our firms. So the red ones, maybe they're the dividend-paying firms, and the blue ones, maybe they're the non-dividend-paying firms. And what we try to do with this support vector and machine learning is we try to separate them by a plane. And that's what that blue line is there. Look, it's called the separating hyperplane. Isn't that a cool name for just, regular kind of a line in there? But what happens and this is kind of a perfect example, notice that there's one blue dot and one red circle dot that is on the dotted line. So those are called the support vectors. And so essentially, the farther the distance between the support vectors and that hyperplane, the greater is the support vector machine learning ability to separate these observations based on their features. Now, this is a super simple example because, there are probably just one or two features. Now, if you throw in, all sorts of other stuff in there, you probably get a more complex kind of a looking graph. But that's really all you're trying to do here, is to, boy, I don't want to use this word because we used clustering before, but we're separating them by these vectors based on the distance between those two. And by the way, those are called margins. And so you can have many features or you can have just a couple of features, but you can get the sense that the machine is doing all the work without any type of economic foundation or theory to support. We're not saying to go ahead and divide these by anything other than whatever that output was. What was the output? Pay the dividend or we didn't pay the dividend. Now, the last part of the reading is on these neural networks, and this is really, really cool stuff. The reading does mention, and if you do any search on this, the most applicable output for these NNs is image and facial recognition. And I want to kind of work through this, but it can be used, of course, to take a look at stock price patterns. And I'll come up with an example here in just a minute about that. But notice what we have. We have some input variables. We have some hidden layers, and then we have an output variable. So we know what these input variables are. So think about facial recognition. What do you need to recognize a face? And remember I said this earlier, this has Jason Bourne and James Bond embedded all in it. And also The Gray Man. I told you guys to go watch that movie. I think it was in that previous reading, or better yet, read the book. Oh my gosh, read the book. Anyway, so what are some input variables? Well, you have the eyes, right? So you have eyes, and so you have the color of the eyes, you have the size of the eyes, and then you can throw the nose in there. What's the size of the nose? Is it a nice little petite nose with all the famous Hollywood actors, or is it maybe a nose that was a boxer and got broken several times? And the mouth and the cheeks and the ears, whatever it is. But then the hidden layer is going to be an algorithm that says something like, okay, let's calculate the distance between the pupils of the two eyes. Oh, now we're getting somewhere. Let's calculate, here I'm making this stuff up, the circumference of the nostril. How about the length between each tooth, right? What kind of teeth? So there's all this stuff. And so taken by itself, it's called a hidden layer. The distance between the two pupils, I don't even know. How far is that? Can I get a ruler out? What is that? Right here, that's 2 inches, right, for me. So think about it. If you know that the pupils are 2 inches, is that going to help identify me? And if you have my face? Well, of course not. But if you combine that distance with the circumference of the nostril and the length of the teeth and the color, the shade of the teeth, and then the lip, and then do I have any moles? Do I have any pimples? Do my ears stick out? My dad was so funny. He would say to us as he was aging, he goes, the one thing that grows on a body is the length of the ear. And sure enough, his ear was like an inch longer than it was when he was 30 years old. It was really funny. And he was always made fun of himself. And it was a great lesson to learn as when he got sick. Anyway, so you got the ears and you got all, but individually, these things, they're not going to help you identify, but in that hidden layer, they take all this stuff together and they say, boom, there's Jason Bourne. He's at the airport and he's running down the airport to try to get a plane. We better hurry up and catch him. So that output is, identifying Jason Bourne. So look in this bottom right illustration. So there's the input layer, there's the hidden layer. And note that not every arrow from the input layer has to go to every hidden layer. And then the hidden layers, then they contribute to the output layer. Now the reading goes on to kind of explain a little bit of the math behind it, although I can't imagine that you would be asked to do any kind of a math. But here we go. Equations to determine those hidden nodes. So H1, H2, and H3 in this case, because we have 3 of them. So look at the theta there. That's known as the activation function, like color of the eyes and distance. So we're activating and we're saying, okay, we found something. Suppose that the airport camera picked up a picture of Jason Bourne's foot. So there's a foot. And so the algorithm is saying, oh my gosh, I don't know what this thing is. It would just throw it out, right? That theta would say, oh no, these are eyes. So let's include, so we're activating, right? And so those X1s and X2s, those are all of the input layers. And then the W's, those things are kind of like weights. They're kind of like probabilities. They're kind of a combination of all that stuff. It's linearity and non-linearity. And so what we're trying to do is just solve that system of equations. Now, I'm way not smart enough to be able to do all that, but you can get the sense that somebody is, and they can figure out how to solve that. So here's another slide, just kind of refreshing what I was saying here. Look at the very bottom block point. Note that weight 122 is the weight relating with the link between X2 and H2. So, X2 might be something and H2 might be something else. And then there might be different weights, 121 or 123 or, however many features that we have. And so think about what this means if we use this neural network to try to predict stock price tomorrow. So we have, a history of stock prices, and maybe these are prices and maybe these are returns. And so we have, 100 days or 1,000 days, whatever it is. And we know from our conversations with time series that, boy, you need to have covariance stationarity or else the model just blows up. Well, here we don't care about covariant stationarity because we're going to combine linearity with nonlinearity, and this network is going to be able to overcome those problems. Yeah, so what are we saying here? Those parameters are chosen through gradient descent. So we're adjusting those parameters to do what? The same thing that I've been talking about all along. Minimize the error of that objective function. So what would be the objective function in our dividend paying firm example? We would say something like, you know what we want to do is that we want to make certain that we're correct 99% of the time. So, just simple math, we're willing to accept a 1% error in that objective function, and it could be almost anything else, as we go down through whatever kind of a model that we're using. Now we do have this learning rate here. This is a hyperparameter that's going to determine that size of the step. So going back here, what are we trying to do? We're trying to put this stuff in a vise and squeeze it so that the error term is at its minimum acceptable value. But we're not going to just squeeze that quickly until it gets there. We're going to squeeze little by little, right? Those of you who are carpenters will know that sometimes that vise doesn't turn very quickly depending on what's in between the two ends, right? If learning rate is too small, it takes longer to get there. If it's too large, then you have no idea what's going to happen there. So remember, we're trying to weigh marginal costs and marginal benefits. Computing time is it's not cheap. So many hidden layers and nodes. It's going to be costly, and it's going to be overfitting. So we'll go back to that regularization concept that we talked about in that previous video, that previous video that tells us that, we don't need all this stuff. We just need some of the stuff, right? Regularization is kind of like sampling. Now, this is fascinating discussion here at the very end of this reading on the confusion matrix. So it sounds like, the name sounds like, hey, let's put a matrix together to confuse everybody. But what it actually does, it should be called let's remove the confusion from our decision. And so look down here at the table. We can have an actual positive and an actual negative down here on the first column, and then going across that top row, what the model predicts. Did we predict positive and did we predict negative? So in the intersection of the greens and the reds, we have a true positive. And in the reds, we have a true negative, then we have a false negative and a false positive. This is a binary classification model. And so this is going to help us eliminate the confusion between what we're going to do. So look, true positive and true negative model correctly predicted, false positive, false negative, incorrect prediction. All right, so what does that mean? Now, here's where I'm going to go ahead and let you guys kind of decide on your own. You can look at these equations, and if you read through them, they kind of make a lot of sense. It might be worth it for you to get out your phone and take a picture of this, because one of the problems at the end of the reading asks you to go ahead and predict, asks you to calculate accuracy and precision and recall. So you ought to be able to know these for the exam. But let's go ahead and work through an example so that you can see how this is done. So we have 1,600 borrowers, 400 of whom defaulted on their loans. All right, so notice that second line there, we use a couple of different models to create a prediction model. We pick a threshold value of 0.5. Maybe we wanted to pick 0.6, maybe we wanted to pick 0.4, but if we're going to pick, if these are going to be binary, default or not default, then we'll probably pick 0.5. All right, so we had one hidden layer, a bunch of other stuff in there. So here's what happens. We've got 150 that were in that second column, and then 300 and 1150. So what does that add? If you sum all those, that gets you to the 1,600. So 100 were true positives, and 1150 were true negatives. So we made mistakes up in the top right corner of 300. We made mistakes in the bottom left corner of 50. So that's a total of 350 mistakes and a total of 1250 accurate predictions. That makes sense? So let's go ahead and do just a little bit of the math. Whoops. And so there's logistic regression, there's the validation sample, there's a neural network training sample, there's the neural network validation sample. So these are some extra pieces of information. And so let's go ahead and make some calculations. So look at the top block point. The values in this confusion matrix have been used to calculate the various evaluation metrics. So we use the math here in these confusion matrices to get our performance metrics of accuracy and precision and recall. And so notice over on the validation sample, and I'm guessing that you would just get a table like this. Boy, look at logistic regression, 65, 64, 36, neural network, 65, 64, 33. I don't know. You could probably just say, and some kind of a general idea that, they're probably super similar. Well, there we go. There's not much difference in the performance. But what can we say? The logistic regression model, higher true positive rate, lower true negative rate, right? Neural network, higher true positive rate, lower true negative rate for the validation data. So you get that from the you get that information from the confusion matrices. And so the question then becomes, what do we do? How do we compare those things? How do we compare those models? And this is with what's known as a receiver operating curve. And it's really just a picture that shows a trade-off of the true positive rate and the false positive rate. So look down at these graphs here, the first row of graphs. So FPR, false positive rate along the horizontal axis, true positive rate on the vertical axis. Now there's only one of these graphs that show up in the reading. We've shown you 4 of them there. So look at that ROC curve. And this concept of the area under the curve, that's 100%, so that's perfect there on the left. And over on the right, that's just totally imperfect. And so you can kind of get a sense of what is going on based on, the second and the third one there. We've got different levels of area under the curve. So let's go ahead and just summarize this. So if the area under the curve is equal to 0.5, the model is no better than random guessing. If it's less than 0.5, then it stinks. The model has a negative prediction value. So you can see that as we move from 100% all the way over to 0% there. And then the bottom row there, this is just taking the positives and the negatives and kind of lumping them on together, kind of taking an average. And that takes us through our learning objectives. So remember what I said after part A, I wanted you to go and quickly work through the handful of problems that we covered in part A. I told you to take maybe 10 or 15 minutes. Well, now I want you to go ahead and take 30 or 40 minutes. It's going to take you to get through those. I think it's 14 or 15 problems there. But what we've discussed in both A and B ought to get you to most of the correct answers. Now, you may need to remind yourself, especially with the entropy stuff, you may need to remind yourself how to do the math. And the confusion matrix, you might need to remind yourself of those equations. But otherwise, you should be fine. So thanks for watching. I had super fun, and good luck studying.